Alright guys, we're going to be going through the example problems for Unit 9 that came from the Zoomal book. So if you could please follow along on your typed out questions as we go, and I'm just going to show you my work. So we're starting with example 17.1, positional entropy. So the first example, A, we have to compare solid CO2 versus gas CO2. And the question is, which of these has greater positional entropy? So if you think about it, the solid CO2, that's just going to take up some amount of space. So here's that solid, right? But then the gaseous CO2 can go all the way around. So if you think about it, there's more places to put the energy. I could have energy here, 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 here. So the gaseous CO2, is going to have higher positional entropy because it has a greater volume. There's more places to stick that energy. Okay, the next example is we have N2 gas at 1 atm versus N2 gas at 1.0 times 10 to the negative 2 atms. And for me, writing this out is really helpful. So my decimal goes 1, 2 over, so this is 0.010 atms. That's atmospheric pressures. So if you think about it, this has less pressure pushing on the molecules. So if I have this N2, like here's an N2, and here's another N2, and here's another N2, right? These are being pushed on by 1.0 atm pressure. So it's keeping them in place. Versus over here, those same three that I drew, molecules, are going to be taking up less space because we have less pressure pushing them together, right? So here's that pressure. So you can see it's not being pushed together as much. So likewise, since these can spread out more, okay, this is going to have the higher positional entropy because we can have energy over here, maybe over here, here, here. This is actually going to take up 1,000 times greater volume, so this will have higher positional entropy. For 17.2, we're going to be predicting entropy changes. So what we want to know is delta S. Is this going to be positive or negative? So in the first, or letter A, it's saying we have sugar solid is converting to basically aqueous, right? So it's in water. We're going to put it in warm water, and sugar dissolves in warm water. If you've ever made hot tea, you've seen this. So we're saying, does the entropy increase or decrease in this situation? Think of it as disorder. So as you have this solid sugar, it's going to be like in a cube, right? It's all packed together. Versus, then you're going to put it in this warm water, and all the particles are going to be moving around, going around. So you have more disorder here, less disorder here. So you end with, so your final is big, so we have big minus little. Because this has big entropy, or lots of disorder. This relatively has little disorder. So when I have a big number minus a little number, this is going to give me positive results. So this has positive change in entropy. The final entropy is larger than what you started with. B says iodine vapor, so iodine here, which is gas, vapor, is going to condense, right, on a cold surface to make iodine liquid. So we have these gaseous molecules moving around all over the place, and then we have them kind of flowing in a liquid. So if you see this relative has big or large disorder, and this has that smaller disorder. So if you're going to do the change, you have small minus big, and that's going to be negative. In 17.3, it talks about in cells assembling large molecules. So maybe you're talking about DNA, which has like an adenine, a guanine, a thymine, a cytosine, an adenine, right? It just made up a random set of base pairs, right? So this would be assembled, and all of these aren't, as we know, these aren't elements, right? These are all molecules. So they're atoms that then make up these molecules, and then they form all these strands, and they have their base pair. So this would match with the T, and this would match with the C. You guys learned this back in bio, right? So it makes this massive structure, and plus these actually aren't attached. They're attached to a deoxyribose sugar and a phosphate backbone. So this has the backbone that it's attached to, and then this part has the backbone that it's attached to, right? So this would make up a large molecule. And one might say that this doesn't follow the second law of thermodynamics, right? That second law of thermo says that the disorder of the universe is increasing. So when we assemble this large molecule, when we have all these bases floating around, and then they all come together to make this organized structure, you're like, well, wait, that is making this more organized. But what you have to remember is this is the system. And then there's the rest of the universe, and that's the surroundings. So when we make this come together, this overall entropy within our system is going down. But when we take those bases, there's disorder in the surroundings, and there must be a greater increase in disorder in the surroundings relative to the decrease in disorder in the system to make the overall universe, the disorder is still increasing. So remember that just because something becomes more organized doesn't mean it's violating the second law of thermodynamics, because that second law is talking about the whole universe, not just right here. So remember, these bases, or the atoms that made these bases, or the atoms that made the phosphate or the sugar backbone, right? They all came from the surroundings, and they left whatever molecule. They made more disorder out here. So to make this happen, this can happen, but still the overall disorder of the surroundings must have gone up more so than how much the system decreased in disorder. In example 17.4, we have two equations, and we're giving the change in enthalpy for each. Okay, both of these are happening at 25 degrees Celsius and 1 atm. And what the problem is asking us for is we want to find the change in enthalpy of the surroundings. Okay, so if we want to find the change of enthalpy in the surroundings, we have this formula that says the change in enthalpy in the surroundings is equal to negative change in enthalpy divided by temperature. Now remember, it's a negative because our change in enthalpy is talking about this specific reaction, but we're caring about our surroundings, so it's going to be the opposite, right? If heat is lost in this reaction, it's gained by your surroundings. As heat is gained in the reaction, it's because the surroundings lost it. And enthalpy is related to heat transfer divided by temperature. Now remember, this temperature is going to be in kelvins, so we do have to change this. We were always wanting to look, oh, is that temperature in Kelvin? If so, bump it up by 273. That'll give you 289 for this guy, kelvins. Remember, I can't even think of a time you would use Celsius. Just always go ahead and convert to kelvins. So for this first reaction, if we want to find the change in entropy for the surroundings, you take negative change in enthalpy for the reaction divided by temperature. So this is going to be negative 125 kilojoules divided by 298 kelvins. And this is going to be, we can see, 0.419 kilojoules per Kelvin. But since this is kilojoules and entropy is in joules per Kelvin, we know that this is going to be 419 joules per Kelvin. Sometimes what's really nice is just to remember unit analysis. So entropy is in joules per Kelvin, right? So you can kind of piece stuff together. If you didn't remember this formula, if you know that it's joules per Kelvin, you can find, oh, this relates to joules, you can get this to kelvins, and you can kind of piece together what to do with your information. The negative sign, again, is because we're talking about the surroundings. So for this equation, same thing, and it's at the same temperature. This equation only works if you're keeping the same temperature and the same pressure. And we said the temperature is going to stay 25 degrees Celsius and the pressure is going to be 1 atm. The pressure doesn't appear in the problem. The whole thing is the pressure has to be constant throughout. So for this guy, right, we've got delta S surroundings. So, and change of entropy in the surroundings is equal to negative our delta H. So that's going to be 778 kilojoules divided by, still using kelvins, 298 kelvins. So this is negative 2.61 kilojoules per Kelvin. And then if we wanted to convert this to joules per Kelvin, remember kilo is 10 to the third. So I can replace that kilo with 10 to the third and say negative 2.61 times 10 to the third, because this 10 to the third means kilo, and now we've got joules per Kelvin. In question 17.5, it's asking when is liquid bromine going to spontaneously turn to gaseous bromine, right? So spontaneous means it's just going to happen. You don't have to do anything to make it happen. We know that it's happening at 1 atm, and we've got our delta H and delta S. These are standardized, right? That's what you see here. So to evaluate if something's going to happen spontaneously, you want to look at this thing called Gibbs free energy. And this is the energy available to do a reaction. Whenever your Gibbs free energy, this guy here, if this is negative, then it's going to be spontaneous. Okay? So that's what you want to look for a reaction. Now it's kind of weird to say when would this be negative, but basically it would be when, since we can see that delta H is positive here, right? So this is positive. So when this piece overpowers the T delta S, when that's going to overpower our delta H. So T delta S, right? This has a positive value I can see. So I know that this minus temperature times change in entropy has to be big enough so that when you subtract it from your enthalpy, you end up getting a negative. Now, the way we can evaluate that is we can say, well, what about when our Gibbs free energy is 0, right? When we're in equilibrium going back and forth, that we can see that if this is 0, and we've got this equation. When we rearrange this, so if I put this on, add this to both sides, then you can see that this converts to, so when this is at equilibrium, so I skip so many letters, it's hard to tell what I'm writing, equilibrium, then T temperature times change in entropy is equal to change in enthalpy. So when this happens, you're going back and forth. But we want to know when would it spontaneously all go to the gaseous state. So then it's going to be whatever temperature is slightly higher than that. So this would create the equilibrium, and then we could say, well, any temperature higher than that would favor our making delta G negative, right? So if we can figure out when these are equal, we can then say, because S is consistent, we know what S is, so T is the one that's changing, so this is all based on the temperature. So if we could say when these cancel each other out and we get 0, then any temperature higher than that makes this side of my, of this statement, this side larger, and your overall will be negative. So we're going to work within this piece right here, especially because we know this and we know this variable. So that leaves only one variable left. So we're going to plug that in. So we've got T equals, let's solve for temperature. I started doing that, but that actually makes sense. So we're going to divide both sides by this, change in entropy. This cancels. And T equals change in enthalpy divided by change in entropy, right? So if I write that out, I've got 31.0 kilojoules per mole divided by 93.0 joules per mole times kelvins. Okay, so if you look at our units, we have a bit of a problem because we can't cancel everything out, right? We need to make this top piece in joules so it'll work out to the bottom. So this is going to be 31.0 times 10 to the third, and this is not proper scientific notation. If I wanted this to be proper scientific notation, sorry, you can't see that, then this would be 3.10 times 10 to the fourth. But since we're just going to plug this into our calculator, I don't really care that much. So joules divided by moles over 93.0 times joules divided by moles times kelvins. And if you notice, I put the kelvins on the opposite side versus here it's kelvins times moles. It's the same thing because they're dividing by both of those. The reason I did that is we can clearly see that joules per mole and joules per mole cancel. So now this is 1 over kelvins on the bottom. So as I do that, if I have this 1 over kelvins as my unit, but it's on the bottom, I'm dividing by this fraction. It's the same thing as putting just kelvins on top. So now I plug this into my calculator and this into my calculator. My temperature is going to be 333 kelvins. At 333 kelvins, my first piece of my equation, my change in enthalpy, is going to be equal to my temperature times change in entropy. But to make it spontaneous, I need this negative, which means this needs to be just a little bigger. So I can say when temperature is greater than, but not equal to, greater than 333 kelvins, then my bromine liquid will convert to bromine gaseous spontaneously. You'll find this is the boiling point of Br2 at 1 atm. All right, so for this one, 17.6, we've got two statements and we're making predictions for each one. Do we think that the change in entropy, so the standard change in entropy, is that going to be positive or negative for each one? So I want to remind you that this is going to be entropy final minus entropy initial. If we look at this, we're comparing, here's our initial versus our final. So we've got a solid, so calcium carbonate, breaking down. This is a decomposition reaction. We have one thing breaking down into two. We've got a solid calcium oxide, and then a gaseous CO2. So if you want to think about entropy, think about disorder or randomness. So this is a solid. These are all, there's specific places where energy can be kept, right? You just have everything packed in. First, over here, yeah, we have another solid. And if we went from a solid to a solid, we wouldn't be able to make any kind of assumption here. But we also have a gas. And that's really what you want to look for with states of matter. Solid, liquid, gas. Remember, when all things are basically relative, solid, liquid, gas is going to have the most entropy. It's got the most disorder. Those molecules are moving around like crazy. So since this has a gas and there's no gas over here, then our final is going to be bigger than our initial for our entropy, our disorder. This has more disorder. So if I look at this, I've got S final is much bigger than S initial, right? So if I have a big number minus a smaller number, then this is going to be positive. So let's look at letter B. I've got 2 moles of gas. No, I've got 3 moles of gas. I've got 2 moles of sodium dioxide and 1 mole of oxygen gas. And that's all converting. This is a synthesis reaction or a combination reaction. I've got things coming together to make one product. So all of these have gas. So that's all, you know, relative as far as the entropy. But this side has 3 moles of gas, and this side only has 2 moles of gas. So if I'm talking about disorder, then this is going to have more disorder, or more places to put the energy, more variations of where we can put our energy, because we have more stuff. So if I look at my delta S, this is going to be my big side, my initial, and this is going to be my small side, my final. So I have a small final minus a lot of initial entropy, a lot of disorder to start. So this is going to be a small number minus a big number. That's going to give us a negative entropy. Okay, so for this problem, for 17.7, we're given an equation, and we want to find the standard change in entropies. So that's the goal for this. So we're given the equation, and we're also giving the values for each of these. Now, one of the things I want to point out, so like in SO2, sometimes I like to write it right under. So this is 248 joules per Kelvin times mole. And that is the entropy for this substance, for SO2. And you might be saying, well, earlier, Mrs. D, you said that entropy is just joules per Kelvin. And that's true as the absolute entropy, but if you're talking about a specific substance, you really have to say how much of the stuff you have. Because the more stuff you have, the more entropy it has, the more places to put all that energy, right? So when we're looking at per substance, remember it's per mole. But you want to get it to just joules per Kelvin. So I have to say, well, how many moles do I have? So this is 2 moles times, because I have the 2 here, this. And then my moles will cancel, and this will get me, so 2 times 248 is going to be 496. Oh, that's not a 4. 496 joules per Kelvin. So that gets us to our absolute, because there's no moles there. And you do that for each substance, right? So if I look at nickel, for example, I've got 2 moles of nickel oxide. Apologies. So nickel oxide is 38, so multiplying, joules per Kelvin times mole. Our moles cancel, right? Okay, this is going to be 3 moles times our oxygen value, which is 205 joules per Kelvin times mole. So for each mole of oxygen, I have 205 units of entropy, or joules per Kelvin, but I have 3 of them. I have 2 moles of nickel 2 sulfide, and then this is going to be 53 joules per Kelvin times mole. And I'm going to divide this in half, and I'm going to add up on each side. So I can see how much entropy do I have to start with, and how much entropy do I have to end with. So I'm going to get out my calculator and do some of this work. So I have 2 times 53, so this is going to be 106 joules per Kelvin, plus 3 times 205, and that's going to be 615 joules per Kelvin. Over here, so I'm just going to check my math. Oh, good, I did it right. And then I have 2 times 38, So this is 76 joules per Kelvin. So if I'm looking at the entropy of my reactants, so S reactants, this is going to be 106 plus 615. So this is 721 joules per Kelvin. Over here, if I look at my entropy of my products, then that's 496 plus 76. So that's 572 joules per Kelvin. I'm looking for my change in entropy though. So that's going to be S final minus S initial. So if I look at that, here's my final, which is my products. So that's going to be 572 joules per Kelvin minus 721 joules per Kelvin. So this is change in S. So change in S is this. If you plug it into your calculator, you're going to get negative 149 joules per Kelvin. Example 17.8 is the same idea. We're trying to find the same thing. Well, it's not the same idea. It's literally the same concept. But now I'm going to show you how to use the official equation. So in 17.7, I wanted to think about it conceptually, why the units work out how they do, and kind of map everything out. But this time I want to show you the more chemistry-y way to do it, right? So we have a new equation, new substances, which means we have new standard entropies. So if you're trying to find the standard change in entropy, then there's this equation that says the sum of all moles of your products times entropy standard of your products minus the sum of all moles of your reactants times entropy of your reactants, which is essentially what we did, right? We did number or moles times each one. I just before worked it out with underneath the equation, and then you flip it later. When you think about change, it's always final minus initial. And this just sets it up as that, so final minus initial or products minus reactants. So if we're to do that, then you're going to look at our products first. So I have 2 of aluminum, and then I look for aluminum, and it's 28, plus 3 times water. So I have 3 waters, so I look up water, and that's 189. And then I have minus, and everything after that's going to be minus, because it's all inside. So then I go to my reactants. I've got 1 of aluminum oxide, and then I go here, aluminum oxide is 51. Minus still, because anytime you then list a reactant, it's always minus 3, because I have 3 hydrogens, and I go to hydrogen, hydrogen is 131. And then you can plug all of this into your calculator, and you're going to get 179 joules per Kelvin. All right, so for example 17.9, we've got another equation. And we want to find the change in enthalpy, the change in entropy, and the change in Gibbs free energy. We're given the enthalpy of formation, and we're given the standard entropy per mole for each substance. So you're given the data to come up with this, you're given the data to come up with this, but then you have to use these bits to come up with your Gibbs free energy. You're also told that this is happening at 25 degrees Celsius and it's kept at 1 atm. We'll need that later. So to figure out my change in enthalpies, we'll do that first. So we're just going to take each substance and multiply it by its molar value and then do final minus initial. So remember, that's always products minus reactants. So change in enthalpy first. So I personally like doing it right underneath because I don't forget information, right? So first going to work through change in enthalpy. So SO2 I find in my list. So I've got 2 of them, and that is negative, the enthalpy of formation, 297, and this is kilojoules per mole to make that. And then my oxygen is nothing to form because it is elemental. Then my products, I've got 2 times, and I've got my moles of SO3. This is 2 moles, by the way. So I've got 2 moles of SO3. Whenever you form SO3 from its elements, it's going to release negative 396 kilojoules for each mole. I've got 2 moles. I've got 2 moles here. So my moles cancel. Moles. So the molar formation on this side is going to be negative 594. So I've got 2 times negative 297. This is kilojoules. Over here, I've got 2 times negative 396. So this is going to be negative 792 kilojoules. Remember, this is final. This is initial. So if I want to find delta H standard, I'm going to do final minus initial. So this gives me negative 198 kilojoules. It's really important to write your units because you want to make sure you have that kilojoules there. Enthalpy is pretty much always written as kilojoules, but entropy is written with joules. So that creates kind of an issue for you later. So now let's look at entropy. We're still going to be doing the same thing, take the molar value, because what we're given is joules per Kelvin per mole. And we want joules per Kelvin. Okay, so we've got SO2, we've got 2 moles of SO2. And then we look on our chart for SO2 that's given in the problem, and then this is going to be 248 joules per Kelvin times mole. For oxygen, I've got 1 mole of oxygen. And when I find oxygen on this, it's going to be 205 joules per Kelvin times mole. In our products, I've got 2 moles SO3 from here. I find SO3 in my chart in my problem, and enthalpy here, so for each mole, it has 257 joules for each Kelvin in our temperature for each mole. So I'm going to add these up to find my overall amount over here. So I have 2 times 248. My moles cancel, and this is going to be 496 joules per Kelvin plus, so this is easy math here. I know my moles cancel, and I've got 1 times 205. We can definitely do that in our head. So overall, my S initial is 701 joules per Kelvin. My S final is going to be 2 times 257. So that's going to be 514 joules per Kelvin. That's my S final. So if I want to find delta S, I'm going to do S final minus S initial. So this is going to be 514 joules per Kelvin minus 701 joules per Kelvin. Not sure what this is on my paper. Apparently I drew on that at some point. So that's going to get me negative 187 joules per Kelvin. All right, so the last bit is to find change in Gibbs free energy. To do that, we have this equation. So this is on your equation sheet, I'm sure, but if not, make sure you memorize it. It's always good, though, to just know equations, because if you have to look it up, you might get a little confused. Remember, we've got temperature here, so this has to be in kelvins. Never put a temperature in Celsius. So 25 degrees Celsius is the same thing as 298 kelvins. You're always adding 273. If there's more decimal places, just FYI, it's 273.15. So if you need to go 2 out, I've never seen it go more than 2 out, but since we don't have anything after the decimal, we don't need to add anything to it after the decimal. So now we're going to plug all our stuff in. So delta G equals. So this is negative 198 kilojoules minus, and then this is going to be our temperature of 298 times negative 187 joules per Kelvin. We're going to put this in kilojoules, because otherwise it's going to be a really big value, because this is so much. So this needs to convert to kilojoules as well. So I'm going to add a conversion factor here. So that means I'm going to multiply it by something that's technically equal to 1, so it doesn't actually change our value. So this has joules on the top, so I want joules on the bottom. But I want this to be kilojoules. Kilo is the same as 10 to the third, or 1,000. So if I put 1,000 on the bottom, then these two things are the same. 1 kilojoule is the same thing as 1,000 joules. These are equal. But now that I've done this conversion, I can get rid of joules, and I'm left with kilojoules. That'll also allow these to add up nicely, because this is kelvins. I forgot to write my K. So my kelvins are going to cancel. So this whole thing, so 298 times negative 187 divided by 1,000 is going to be left in kilojoules. Okay, so let's do that math. So I've got 298 times negative 187 divided by 1,000. That gives us negative 55.726. I only get to keep 3 sig figs, because I have 3 here, 3 here. This is an absolute. This is 0.0000. This has an infinity amount of sig figs, so that doesn't count. So I only get to keep 3 sig figs. So this is negative 198 kilojoules minus negative, so this is 55.726. So I've got a 7, and then the 2 gets dropped because I only have 3 sig figs, and 2 doesn't bump anything up before it. This is kilojoules. This ends up giving us, so this becomes a plus, right? So this becomes negative 142 kilojoules. This is spontaneous. This is how much energy we have to do that reaction. In 17.10, we've got 2 equations. We've got the combustion of carbon in the diamond form. We've got combustion of carbon in the graphite form. And it's given our Gibbs free energy changes for each of these. But what we want to know is, what about just when diamond converts to graphite? So we did this before when we were talking about enthalpy. We can actually rearrange equations to almost add up our equations. So we know we want to start with diamond, so this has to be a reactant. And we want graphite as our product, so this has to be a product. So we're going to switch this second equation. So this now becomes CO2 gas converts to carbon in the graphite form plus O2 in the gaseous form. And our Gibbs free energy for this reaction is going to have the opposite value because we flipped the equation. So we're getting rid of this. We flipped that to make our graphite a product, so it matches what we want. When we add up these equations now, that line went a little rogue there. I can see that my CO2 gas has a reactant and 1 mole as a product, so those will cancel. I have 1 mole of oxygen gas as a reactant and 1 mole of oxygen gas as a product. I have 1 mole of carbon in the diamond form as a reactant, which is what I want. I have 1 mole of carbon in the graphite form as your product, that's here. And I can just add this up to figure out the Gibbs free energy. So now this is going to be negative 397 kilojoules plus positive 394 kilojoules. So overall, this is going to have negative 3 kilojoules Gibbs free energy for this reaction. Now you might be saying, oh my gosh, if this has a negative Gibbs free energy change, then this is a spontaneous reaction. So diamonds will spontaneously form graphite. Uh-oh, that's not good if you got any diamond jewelry, right? But if you have any diamond jewelry, you might notice it hasn't just randomly converted to graphite, which is like what's on the tippity top of pencils. You generally call it lead. It's not lead, it's actually carbon. And that jewelry y'all are wearing isn't going to just spontaneously do that in an instant. Remember that just because something's spontaneous, I want to point out that doesn't mean it happens quickly. That is referring to kinetics. This is just saying, yep, it's going to happen, but it is so slow, this reaction. And it has nothing to do with the value here. So this is just saying, yep, it'll happen on its own, has zero influence on the kinetics. You could go through the kinetics, you'll find out that this reaction is really, really, really slow. So you don't have to worry about that, those diamond earrings you have converting to something you can write with on a piece of paper anytime soon. You can also see that graphite isn't going to spontaneously form into diamond. You have to put in energy to make the reverse thing happen. So that's, if you've ever learned how diamonds are formed, they're formed underground in a whole bunch of pressure, and that pressure is putting in the energy to be able to make this reverse reaction happen. In this reaction, we want to find the change in Gibbs free energy here. Okay, so that's the goal. We're given an equation. On your sheet, you're given a chart with the energy of formation, the Gibbs free energy of formation of each of these substances. And we can see right away that oxygen is elemental. So remember, whenever you're talking about formation, you're talking about the elements coming together to make up that substance. So since this is in its elemental form, this is going to have 0 for its value. I'm going to divide it up so we can have our initial and our final separate. So let's start over here. So this is 2 moles of octane. And then in our chart, I can see that when I form octane, it's going to release 163 kilojoules for each mole it makes. Since I've made 2 moles of it, I'm going to have 2 times 163, and then I have to remember my negative. This is going to be negative 326 kilojoules. Now notice my moles cancel, right? I've got moles and then per mole, so this is just negative 326 kilojoules. Over here, the Gibbs free energy of formation for carbon dioxide. So I have 2 moles of this. On my chart, I find CO2 gas, and that's negative 394 kilojoules are released for every mole. I also have 4 moles of water in the gaseous form. Water in the gaseous form, according to the chart given to you in the problem, is negative 229 kilojoules per mole. So I have 2 times negative 394, so this is going to be negative 788. My moles cancel, I'm left with kilojoules. Plus, I've got 4 moles, moles cancel, times negative 229, so this is going to be negative 916 kilojoules. I can add these up, and I can see that I have negative 1,704 kilojoules on my product side. So this is final, this is initial. So it's always final minus initial. Negative 1,704 kilojoules minus my initial. Now don't get confused by this negative here. It's minus your initial, not minus is already included. So it's minus negative 326 kilojoules. So minus negative 326. This is going to give us negative 1,378 kilojoules. So that is the change in Gibbs free energy for this reaction. In example 1712, we have this reaction, and you're told a chemical engineer wants to know how feasible it is to make this, the ethanol. So in this problem, it doesn't give you any values. It expects you to look them up in the appendix in the back of the book. I'm going to go ahead and give those to you. There are no values that you would be expected to memorize on the AP exam. They will always give you whatever the energy of formations are. However, they might give you more values than what is given. Like they might give you water as a gas, water as a liquid, and you have to make sure that you pull the liquid value for water, right? If you're talking is not a word. If you're talking about C2H4, same thing. They might give it to you as a gas and a liquid, or they might give you, a whole bunch of substances. You have to pull it out. They might give you something with a similar formula, and they want you to make sure that you're grabbing C2H4. So don't grab C2H6 gas, right? Make sure you're reading the right substance. All right, so we want to find if this is spontaneous. We're looking, is it positive or negative? So that's how we're going to determine feasibility of this reaction. We're going to divide up our products and our reactants and our products, because this is going to be our initial side, this is going to be our final side. All right, so we have 1 mole here, 1 mole here, 1 mole here. So that's great because we don't have to do that much math. So the Gibbs free energy of formation of C2H4 as a gas is 68 kilojoules per mole. But I only have 1 mole, so that's going to cancel, right? It's basically like saying 1 mole times, but I'm lazy and I don't want to do that each time. So I'm just going to get rid of the moles. Water as the liquid form is negative 273 kilojoules per mole, but I only have 1 mole, so I only have this negative 273 kilojoules. C2H5OH as a liquid is negative 175 kilojoules per mole. I only have 1 mole, so negative 175 kilojoules. I'm going to combine these because I need to combine my reactants to find out how much energy of formation is just on my reactant side. So this is negative 169 kilojoules. To do all my math, I'm going to do final minus initial. So delta G under standard conditions, and these are all formations under standard conditions, negative 175 minus my initial. These are both kilojoules. So overall, this is negative 6 kilojoules. So this is spontaneous. Our chemical engineer is in luck. It is spontaneous under standard conditions. So up until this point, we've been talking about standard conditions. But now we want to know the change in free energy for real. Notice that little degree sign, which stands for standard, has gone away. So this is what we want to find. When we're doing this, there's an equation that we use, which is the change in Gibbs free energy for realsies, basically, is the standard change in Gibbs free energy. And then we have this qualifier that brings it into real conditions. So we have R, which is our gas constant, temperature in Kelvin, and then the natural log of Q. So this is that reaction quotient that we learned about before when we were talking about equilibrium. So we're bringing this guy back, okay? So this is how, whenever we add this to our standard, and there's lots of background math that you do not need to know, this brings it to normal delta G conditions, so change in Gibbs free energy. Now this didn't give us our values in the problem. The book that I'm using expected you to look in the appendix to look them up, but I'm going to give them to you, right? So, okay, so we're going to find this first. That's what I meant by, sorry, values it didn't give you. And then we're going to do this part second. So just that's our plan of attack. So we're going to use the energy of formations for each of these substances. Now I want you to think about, without looking anything up, which of these energy of formations do you already know? You should have said H2. H2 is an elemental form. So this has no energy of formation because it's already formed. It's talking about how much energy is gained or released when you form that compound from its elements. This is its elements. So it's forming itself. It's already done. You don't need to release or take in any energy to make it. It is what it is. The energy of formation of carbon monoxide as a gas is negative 173 kilojoules. The energy of formation of CH3OH as a liquid is negative 166 kilojoules. Now that would be kilojoules per mole, but we only have 1 mole of each substance, so we can ignore the per mole. So now I can find the standard change in Gibbs free energy. So that's going to be our final minus our initial, minus negative 137, and this is all kilojoules. And then when we do this, when we get our final answer here, we're actually going to get rid of kilojoules. The reason for it is our R is in joules. So we want to go ahead and standardize that. So this is going to be negative 166 minus negative 137. So this would get us negative 29 kilojoules. But I want this to be in joules because my R has regular joules in it. This is a step that kids often forget. When you're using this equation, you always want to do it in joules because of our R. So this is going to be negative 29 times 10 to the third joules, but you want to put it in proper scientific notation. So this is negative 2.9 times 10 to the fourth. Remember that 29 is 10 to the first, so I have 10 to the first and a 10 to the third, and that's how you get this. 29 is 2.9 times 10 to the first. I can explain that a little bit better. 29 equals 2.9 times 10 to the first. So if I have 29 times 10 to the third, that's the same thing as 2.9 times 10 to the first times 10 to the third, and we add these up. This is just a little side note if you weren't able to quickly convert that. All right, so back to the problem. So now we have our standard change in energy. So we have this, and now we have to do that second part that I promised you we would do. So R is equal to our gas constant, and this is given to you on the AP formula sheet. Okay, and then our temperature, we were told in the problem that this happened at 25 degrees Celsius. But remember, we never use Celsius, so plus 273, and that's going to give us our kelvins. So this is 298 kelvins. And then we're going to do the natural log of Q. So we need to find Q. This is our reaction quotient, so you're doing products over reactants. So we were given the pressure of each. So in the problem, it talks about that the carbon monoxide has 5.0 atms and hydrogen gas has 3.0 atms. And we're converting this to liquid. So liquid is not going to have any atmospheric pressure because that's only in gas. So 1 over 5.0 times 3.0 squared. And we have a squared because we have 2 here. When you do this, you're going to do 1 divided by parentheses 5 times 3 squared, or 9 if you want to do it all at once. And this is going to get you 2.2 times 10 to the negative second. So we're going to plug all this stuff in together. So delta G equals my standard Gibbs free energy change, negative 2.9 times 10 to the 4th joules. I hope I have room to write all this. Plus, R is, I'm definitely not going to have room to write all this. Let's write down here. Sorry. Delta G equals. So we're using this equation. So first is our standard. So this is negative 2.9 times 10 to the 4th joules plus my R is, so let's do 8.3145 joules divided by kelvins times moles. And then that is times our temperature, which is 298 kelvins, times the natural log of Q, which is 2.2 times 10 to the negative second. Okay. I also want to note that this delta G standard happens for every mole reaction, because it's for that whole thing. Sometimes you just write the joules, but remember this is for every time this reaction happens once, so per mole reaction. Our kelvins are going to cancel. I have to do this in the calculator, so natural log of 2.2 times 10 to the negative second. You would not be expected to do this in your head. This would be a free response, if anything. So this is going to get you can plug all of this into your calculator. And then this is going to get you negative 38 kilojoules per mole per reaction. So in problem 1714, we have the synthesis of ammonia reaction, and we have 2 different conditions. And what we're talking about here is for each of these, we're going to analyze what shift in equilibrium will happen, if any. Will we have a right shift or a left shift? So let's go over what to think about here. So we're given a bunch of information. I've mapped it out a little differently than what it says in your problem. So if you look at what I typed out, what I got from the book, it looks a little different from this. So I just put the atmospheric pressures for each thing under their substance. So like the pressure of nitrogen was listed second, but I went ahead and put it right under nitrogen, okay? Here's our standard energy change for the reaction. But if we're talking about this, remember this is what they currently have at the beginning, so the reaction quotient. This isn't at equilibrium, and we want to know what's our standard. So the way we're going to analyze this is not to look at standard, to look at the actual delta G and to see what's going on there. Remember, if delta G is negative, then it's going to go ahead and go forward. If it's positive, then we know that the reverse reaction is spontaneous, so we'll go backwards. If delta G is 0, then it's already at equilibrium. So, okay, so let's analyze. Remember, our equation to relate delta G non-standard to delta G in standard conditions. So delta G equals standard change in Gibbs free energy plus RT ln Q. So for each of these, we really want to look at RT ln Q. The other thing is, remember that R is always it has joules in it, not kilojoules. So we want to convert this to joules, not kilojoules. So delta G standard, we're actually going to make this negative 33.3 times 10 to the third joules per mole. And then we need to make this standard scientific notation. So this is negative 3.33 times 10 to the fourth joules per mole. So I'm just kind of working that out right now so we don't have to come back and do that later. For both of these, we're going to analyze RT ln Q for each situation. R and T are going to be a constant, so let's do that. So R, we know that R, we looked at it the last problem, plus it is on your equation sheet. This is 8.3145 joules per Kelvin times mole. And temperature, we're given 25 degrees Celsius. Remember, we have to do plus 273. So this is 298 kelvins. When I multiply these together, 8.3145 times 298, so this is going to be 2,477. Our kelvins cancel, so this is joules per mole. So that's RT. For both conditions, remember our delta G standard stays the same and our RT stays the same. It's just the ln Q that changes. So it's just kind of nice to have stuff set up ahead of time for this. For condition 1, Q is going to be, so you have your products raised to the power of their coefficient. Let me zoom this out a bit so you can see it. Okay. Divided by reactants raised to their power. So Q is going to be the pressure of ammonia squared. So this is 1.00 squared divided by our reactants pressures to their power. So nitrogen is 1.47. It's raised to the first power, or it stays the same. And then hydrogen is 1.00 times 10 to the negative second to the third power, because we have a 3 coefficient. 1.00 times 10 to the negative second raised to the third power. When I plug all of this into my calculator, I'm going to get 6.80 times 10 to the fifth. So that's Q sub 1. Okay. Oh, that makes it looks like it's square. Let's do Q1. So to find delta G1, it's going to be our standard G. So this is negative 3.33 times 10 to the fourth joules per mole plus I don't know why I keep saying my second number first. 2,477 joules per mole. And then it's multiplied by a number. So ln of Q has no units to it. It all keeps the joules per mole from here. So this is going to be the natural log of 6.80 times 10 to the fifth, which I can't do that in my head. So I've got 2,477 times the natural log of 6.8 to the fifth power. So this is plus 33265.73369. Okay, and this, so if I put this to the fourth, okay, well let's put this 3 sig figs so they match up. So this ends up being, 3.3, so 3 sig figs, 1, 2, 3, this 6 bumps that to a 3, times 10 to the fourth. This is joules per mole. I have negative 3.33 times 10 to the 4th joules per mole. So when I add up these two numbers, notice this ends up being 0. So since my change in energy is 0, that means that the forward and the reverse reaction are equal because I'm not changing in energy at this point. So this is already at equilibrium. There's no change in energy. So that's because the forward and reverse reaction are the same, are happening at the same rate. So let's talk about condition number 2. So delta G2 is still going to be that negative 3.33 times 10 to the 4th joules per mole, plus I still have my 2477 joules per mole, but now I need my next Q, so times the natural log of whatever Q is. So let's figure out what Q is. So Q2 is going to be, so we have, oops, can't see that. Remember our products, so now we have 1.00 squared divided by 1.00, that's nitrogen, so there's not raised to any power, and 1.00 hydrogen is raised to the 3rd power, but it really doesn't matter because it's all 1, so this is going to be 1.00. So this is the natural log of 1.00. And as you know, the natural log of 1 is going to be 0. So this whole thing is 0. When you look at this, that means the real change in Gibbs free energy is the same as the standard Gibbs free energy, which is negative. So since this is negative, overall, my change in energy is going to be negative. I didn't add anything that was big enough to overcome it. Then it's going to be spontaneous, which means it's going to have a right shift. It's going to go forward. So we can say a right shift. You could say it's going to form product. It's going to produce more ammonia. There are lots of ways to word it, but this tells us it's spontaneous, which means the forward reaction is going to happen. Had this been large enough to overcome this negativeness and overall made this positive, then we would have had a left shift because the spontaneous reaction would be the reverse reaction, right? So if it's negative, then it's going forward. If it's positive, then we know that the reverse reaction is negative, and that would happen. So since this is negative, we know that it spontaneously goes forward. In our last problem, 17.15, we've got iron combining with oxygen to make iron oxide, or rust. And what it wants is the equilibrium constant, so that's K. And you're like, whoa, we've only used Q. But if you remember, at equilibrium, so at equilibrium, Q equals K. And what we just went over is that we have this condition plus RT ln Q. When the real change in energies, Gibbs free energy, is 0, then we're at equilibrium. So for this to be at equilibrium, delta G equals 0. So this is 0 equals the standard Gibbs free change of energy plus RT ln Q, right? But now that we've made this equilibrium, we say this is actually K. And then from here, we can say, well, this is equal, so this is equal to the opposite of whatever this is. So when you add them up, they cancel each other out. So like if this, it's not going to be you, but like let's say it's 3, then this has to be -3, right? So if this is 3 and this is -3, they add up to be 0. If this is 2 and this is -2, they add up to be 0. If this is 540, and this is positive 540, they add up to be 0. So whatever your standard Gibbs free energy change is has to be the opposite in sign of RT, ln, and we use K because we're talking about at equilibrium. So if we want to find, remember this is the goal, to find K. We know the temperature from the problem, it happened at 25 degrees Celsius, which we know to make 298 kelvins. We know R, we need to find delta G, the standard delta G. But we're not given that. We're given standard enthalpy of formation and the standard entropy. So we need to do our equations that we did up here with our initial and final to work through those. So first, let's talk about delta H of formation. We're going to use those to find change in enthalpy. So our iron from our list, if you look at the problem that I typed out, so we know that iron, well, actually we don't need our list at all, I'm sorry, we don't need this because it doesn't take anything to form iron, right? It doesn't take anything to form oxygen, they're elemental. Iron oxide, so the formation of iron oxide, we have 2 moles in this, and we're going to multiply it by what we got in our chart, which is negative 826 kilojoules per mole. So when we have 826 times 2, that's going to get us, so this is negative, because I have a negative 826, 1,652 kilojoules. We have final minus initial, well, I have 0 as my initial. So delta H equals, and this is standard, apologies, forgot my standard, final minus 0, because that's overall 0 over here, so negative 1,652 kilojoules. I can also make this into joules because later my entropy is going to be in joules. So this is negative 1.652 times 10 to the, so this would initially have just 3, and then I have 3 more because of the kilo, 6 joules. Let me explain that just a little more just in case. So this has 2 parts. It's got the number and the unit, or coefficient and unit. So if I just put the number into scientific notation, that's negative 1.652 times 10 to the boop, 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 third, and then kilojoules. I'm going to take out the kilo because times 10 to the third, that is from kilo. So this is from the number. See how I've moved my decimal? This needs to be multiplied by 1,000 to get to my original. So then when I'm multiplying 2 numbers with the same base raised to a power, I add up my exponents. This is negative 1.652 times 10 to the 3 from the number and 3 from the kilo. Okay. So now I can use my my entropy, my S, right? S standards, so I can find overall delta S. So first I'm going to do iron, and I'm kind of moving everything over just because I wrote this stuff here. So for iron, I've got 4. Write all my information, 4 moles, and I'm going to multiply that by, iron is 27 joules per Kelvin times mole, plus, and my other reactant is 3 moles of oxygen. So I'm going to look up oxygen on my chart, and that is 205 joules per Kelvin times mole. I don't have room to write my products, so I'm just going to write that these are my reactants so I don't get confused. So this is 4 times 27 plus 3 times 205. So this is 723. Are my moles canceled? And this is joules per Kelvin. This is for reactants. Now let's do my products. And again, usually I would do this right underneath, but because I wrote all this stuff over here, I'm just kind of adjusting how I write things. So usually I would write it right under and do that line. So I have 2 moles of iron oxide, and I'm going to multiply it by their entropy. I always have to think, is it enthalpy? Am I talking about an H? Do I have to add that H in, or is it entropy? So S is entropy. And iron oxide is 90, and I got this number 90. It was given to us in the chart in the problem. So now my moles cancel, and this is going to give me 180 joules per Kelvin. So if I want to find the change in entropy standard, so that's going to be final, or products, minus initial, or reactants. Remember, reactants are what you start with, products are what you end with, so final minus initial. So this is going to be 180 joules per Kelvin minus what I started with, 723 joules per Kelvin. So when I do this, I'm going to have 180 minus 723, and that gives me negative 543 joules per Kelvin. Okay, so now I want to find, because again, I want to use the standard Gibbs free energy change. So we have an equation to use, and that's delta G standard equals delta H standard plus, minus temperature times delta S standard. All right, so we have delta H standard to change. So we did that one first. It's up here. So this is negative 1.652 times 10 to the 6th joules minus 298 kelvins times our delta S, which is right here. I'm going to rewrite this so I have a little more room. So I had negative 1.652 times 10 to the 6th joules minus my temperature, 298 kelvins, times, now I have my standard change in entropy, which is negative 543 joules per Kelvin. My kelvins cancel, so this is 298 times negative 543. This stays the same. Negative 1.652 times 10 to the 6th, not negative, joules, minus negative 161,814 joules. So 1.652 times 10 to the 6th minus negative 161,814. It occurs to me I should have probably just plugged it right into my calculator here. Why are we doing more steps? So if you plug it all in here, negative 1.652 times 10 to the 6th minus, let me just put this in brackets. It's going to eliminate steps, eliminate places to make mistakes. So this is going to be negative 1490186 joules. Okay, and we're going to just make this into scientific notation. We can only keep 3 sig figs. So this is, let's make this bigger down here. This problem is a doozy. Negative 1.49. You can see I made some mistakes there. times 10 to the 6th joules. So again, and I'm going to relabel, this is the change in entropy. Not that. The change in Gibbs free energy standard. So now I need to go back to my equation. Remember, change in Gibbs free energy standard is equal to negative RT ln K. So this is why it's really important at the beginning of the problem to write out what the heck do you need. So you need K. And all of this, there's so many things that we've solved for that you might be like, oh, I finished. I solved for that variable. I solved for that variable. But no, we've done all of this work and we still haven't gotten to K. So we know that delta G change standard equals negative RT ln K. Okay. We also know that we know R, we know T, so we really, ln K is the whole big shebang. So this is going to be, we want to solve for ln K. Let's rewrite this then. Ln of K equals delta G standard divided by negative RT. When you do this, here, I'll show you, sorry, I didn't mean my paper to be underneath so hard. So there we go. This means I've got negative 1.49 times 10 to the 6th joules divided by RT. So R is 8.3145 joules per Kelvin times mole. And T is our temperature, so times 298 kelvins. This is joules per reaction, okay, per mole per reaction. So my joules per mole cancel, my kelvins cancel. A lot of times we just don't write the per mole per reaction situation here. So this is negative 1.49 times 10 to the 6th divided by parentheses 8, and this is negative R, negative 8.3145 times 298. So this is going to get us 601.36. We're going to do 3 sig figs, that's all we have, so these go away. So the ln of K is 601. If we want to find K, remember this is the log to the base E. K equals 601. So that means E raised to the 601 power is equal to K. This is way, I think, beyond what we might see on the AP exam, all these steps. Like, they wouldn't expect you to do E raised to the 601 power, but any piece within this might be, is totally fair game, including this bit at the end here that gets kind of complicated. So that's why I thought it was really important to do this problem. And this is where we end for this unit, guys. Let me know if you have any questions. Remember, we can schedule tutoring. If you need it, you just let me know what you need, and I will help as best I possibly can. All right, I'll talk to y'all soon.